This is GATE 2014 set to EC question number 32. In the figure shown, the capacitor is initially uncharged. Which one of the following expression describes the current IT in milliampere for t greater than 0? This is the figure, and for NPTEL reference you can refer to lecture number 14, capacitors relationship of voltage and current and initial condition of the NPTEL course Network Theory by Professor Taposh Kumar Bhattacharya, Department of Electrical Engineering, IIT Kharagpur, and the YouTube lecture link is given here. Useful data is that using final value theorem, the capacitor voltage as a function of time can be written as the final voltage of the capacitor at t tending to infinity plus the difference of the initial and the final voltage of the capacitor into e to the power minus t by tau, where tau is the time constant represented by R equivalent of the circuit into C. The capacitor at steady state also behaves like a open circuit, and the voltage across capacitor cannot change instantaneously. Coming to the solution, it is given in the question that the capacitor was initially uncharged. Now this means that Vc0 minus equal to Vc0 equal to Vc0 plus equal to 0, because the capacitor was initially uncharged, and since the capacitor cannot change its voltage instantaneously, so it will remain the same at all these intervals at equal to 0, 0 minus and 0 plus, and it will be 0. So now if it is 0, and also the capacitor at steady state behaves like open circuit. So now see, since the capacitor is like this, drawing the configuration once again, it is behaving like open circuit, which means that this is 2 kilo ohm, this is 1 kilo ohm, this is 5 volts, and hence at steady state this capacitor becomes open circuited. So Vc at infinity final, so this is can be determined by voltage division rule, which is 5 into 2 by 2 plus 1. The kilo and kilo will be cancelled and will be remaining with 10 by 3, which is 3.33 volts. Now applying the final value theorem, Vc of t equal to, as you see in the final value theorem, so applying final value theorem, it comes Vc of t equal to Vc of infinity plus Vc of 0 minus Vc of infinity e to the power minus t by tau, where tau equal to R equivalent into C. R equivalent can be determined by replacing this voltage source with a short circuit. It is with its internal impedance, and 1K and 2K comes in parallel, and the R equivalent here, as seen from this side, is R equivalent equal to parallel combination of 2K into 1K by 2K plus 1K, which is 3K. So this is 2 by 3K, and this tau comes out to be 2 by 3K into 10 to the power minus 6, because 1 microfarad is the capacitor value, so 2 by 3 millisecond. So now applying this theorem, Vc of t equal to Vc of infinity. Vc of infinity is determined as 10 by 3 plus Vc of 0, which is 0, minus e to the power minus Vc infinity is 10 by 3 e to the power minus t by 2 by 3 milliseconds. This is coming out to be Vc of t equal to 10 by 3 into 1 minus e to the power minus t by 2 by 3 milliseconds. Now in the problem, the voltage across the resistor 2 kilo ohm, V2 kilo ohm, equal to Vc of t, which is equal to 10 by 3 into 1 minus e to the power minus t by 2 by 3 millisecond. Now the I through 2 kilo ohm equal to V through 2 kilo ohm by 2 kilo ohm by Ohm's law. So this is coming out to be 10 by 6 kilo ohm 1 minus e to the power minus t by 2 by 3 milliseconds, which is equal to 5 by 3 into 1 minus e to the power minus t by 2 by 3 milliseconds milliamperes. So tau equal to 2 by 3 millisecond, and this is 5 by 3 1 minus e to the power minus t by tau in milliamperes. So option A is the correct option.